All right, so welcome to Math 409 problem solving. This is lecture 12. And what I wanted to do for today is just continue a little bit on generating functions and talk a little bit about the circle method, Fubini's theorem, and some opportunities for those of you who are interested in mathematical writing. So we saw generating functions multiple times. We saw that they were very useful in studying the Fibonacci numbers. They give us a closed form expression for the nth Fibonacci number where you don't have to go through all the additions. And as a nice exercise, tell me, is it feasible to calculate 1,000 Fibonacci numbers from scratch before you graduate? We then saw the generating functions useful in studying the Catalan numbers. The Catalan number recurrence was a lot more complicated, but miracle of miracles, somehow at the end of the day, we got a nice closed form expression. In general, it is extremely hard to get closed form expressions when you're doing problems like this. It's extremely rare. Does anybody know which class I believe is the greatest lie or the greatest misleading class in college? You come out of this class thinking you can do something, but you can't. Yes, which calculus? No. Calc 2. Calc 1, differentiation is easy. I cannot stump you on a differentiation problem. I can piss you off, that's easy. I can give you a problem that you don't want to do, but you can just keep hacking away with the standard rules of differentiation. Integration is completely different. I have to really work to give you a problem that you can integrate in closed form. So, I mean, Calc 3 is also an acceptable answer. It's even worse than Calc 2. So for generating functions, a lot of it comes down to, can we get a closed form expression? So there's a lot of different generating functions in mathematics. And one of the things I want to do with this class is this is a springboard class to show you a little bit what's out there. And so what I'll start with is the Viemann Zeta function. And if you've never seen the Viemann Zeta function, it is something you absolutely need to see before you graduate. So we define it as zeta of s is the sum, n goes from 1 to infinity of 1 over n to the s for the real part of s greater than 1. Okay. Out of curiosity, how many people have never seen the Viemann Zeta function before in a class? Okay. This is one of the most useful functions in all of mathematics. It turns out, I'm actually going to put a colon here. This is how we indicate a definition. It's defined this way by the fundamental theorem of arithmetic. It turns out it equals the product over the primes 1 minus 1 over p to the s inverse. So this function connects the integers with the primes. So it's 2020 right now. What is the next integer after 2020? Yeah, this was an unacceptable delay. All right, let's see if we can do better. After 2021 and after 2022? Yeah, it's really not that hard. You should, of course, know when you go into taking a competition like the Putnam, you should know is 2022 prime. All right, this is a pretty easy one. 2022 is not prime. You should know the factorization of 2022. It is much harder to find the next prime from the previous. And so the hope is that by looking at this function, we can pass from knowledge of the integers to knowledge of the primes. There is no closed form expression for the location of the nth prime, but there is a closed form expression for the location of the nth integer. Can anybody give me the formula for the location of the nth integer? F of n equals n. Yeah, it's really not that exciting. We know all about the gaps between integers. How far do you have to wait till you get to the next integer? 1, right? Everything is known. So the hope is maybe by knowing things about the integers, we can pass the things about the primes. And so there's a lot of ways we can do it. So we have zeta of s is the sum of 1 over n to the s, n goes from 1 to infinity. It's the product over primes 1 minus 1 over p to the s inverse. Your real part of s greater than 1 so that things converge. As s goes to 1 from above, the sum n goes from 1 to infinity of 1 over n to the s goes to the harmonic series. The sum n goes from 1 to infinity of 1 over n. What do we know about the sum of the harmonic series? Diverges. Therefore, infinitely many primes, else the product is finite. So here's just one application of the Riemann zeta function. We get that there must be infinitely many primes, because if there were only finitely many, then as s goes to 1, that product would be finite. Now, we actually know a little bit more. The sum n less than or equal to x of 1 over n is approximately what? It's approximately log x. So let's say the sum n less than or equal to x of 1 over n to the s is approximately the product over primes less than or equal to x of 1 minus 1 over p to the s inverse. All right? Do you think this is legitimate? What do you think? Reasonable, unreasonable, maybe somewhat reasonable? When I expand things out, the way I expand 1 minus 1 over p to the s out is I use the geometric series formula. So 1 minus 1 over p to the s inverse is equal to 1 plus 1 over p to the s plus 1 over p to the 2s plus 1 over p to the 3s plus dot, dot, dot. If I expand this out, I get all numbers whose prime factors are at most x. And on the left-hand side, I get all numbers that are at most x. So which do you think is larger, the left-hand side or the right-hand side? The right-hand side. So we know that the left-hand side will be lower than the right-hand side. But the hope is maybe they're roughly of the same order of magnitude. Okay, let's just see what we would get. So if we look at the log of the sum of n less than or equal to x of 1 over n, and let's do s equals 1. Yeah, let's say that's roughly the log of the product p less than or equal to x of 1 minus 1 over p to the s inverse. So what is this approximately equal to? The log of the sum of 1 over n for n up to x. This is approximately what? Not x. What's the sum of 1 over n up to x? It's approximately what? So it's about log x. Now, what's the log of a product? Sum of the logs. So this would be approximately negative sum p less than or equal to x log 1 minus 1 over p to the s. But the log of 1 minus x by Taylor is approximately negative x. And I guess I've dropped the s. So this is approximately negative sum p less than or equal to x of 1 over p with a minus sign. So the sum p less than or equal to x of 1 over p is about log x. So not only do the sum of the primes diverge, there's infinitely many of them, we have some rough idea of how quickly. This is not fully rigorous. These two expressions are not equal, but I'm trying to just give you a sense of what you can do. And just the powers of generating functions. The other one, which I truly love, is zeta of 2 is the sum, and it goes from 1 to infinity of 1 over n squared is the product over primes 1 minus 1 over p squared inverse. Does anybody know the value of the sum of 1 over n squared? Pi squared over 6. There's a lot of beautiful proof. Okay, so this is pi squared over 6. What kind of number is pi squared over 6? Irrational. This is irrational. therefore infinitely many primes. So why must there be infinitely many primes?
Each factor on the product is rational.
And if there are only finitely many primes, the finite product of rational numbers is rational. As product would be rational if finite. So, again, here's another proof of the infinitude of primes, the basic building blocks of mathematics. This also leads to the worst paper I ever wrote, although by the time I published it, I made it better. It turns out that there's ways that you can quantify, and if people are interested, we can talk about this later in the semester. Just send me an email. You can quantify how irrational a number is. And certain numbers are more irrational than others. Does anybody know the most irrational number according to the standard metric? It is the golden ratio, the golden mean. It's the hardest number to approximate well by rationals. It turns out pi squared is not a horrible number to approximate by rationals. And we actually have a result about how well you can approximate it. And so I thought it would be interesting if you could use our knowledge of how irrational pi is, or pi squared is, to get a result about how many primes are there up to x. And so we talked about Euclid's proof of the infinitude of primes earlier. Did we do that in this class, or was that the other class I taught? Okay, has everyone seen Euclid's proof of the infinitude of primes? All right. This is a proof you need to see, Euclid. There exist infinitely many primes. If not, say P1 through Pn are all of them. Consider their product and add 1. If prime, list wasn't complete. And then if composite, it's not divisible by P1, P2, ... Pn, as all have remainder 1. So there exists a new prime. This is one of the oldest proofs that's still used in mathematics, over 2,000 years old. With a little bit of work, leads to, more than log x primes up to x. The sequence grows, unfortunately, very slowly. But you can use this to prove that there's at least log x primes up to x. I was wondering, can I use the irrationality knowledge of pi squared to get some statement about how many primes there are? We showed that the sum of 1 over p is at least log x. So there's infinitely many primes, but there's so many primes that the sum of their reciprocal grows like log x. Are there infinitely many perfect squares? Yes. What's the formula for the nth perfect square? N squared. But if you look at the sum of 1 over n squared, that converges. So even though there's infinitely many perfect squares, there's so few of them that the sum of their reciprocals converges. There are so many primes that the sum of their reciprocals diverges. And I was curious to see, could I actually get a result about how many primes there are up to x by using knowledge of the irrationality of pi squared over 6. And I actually proved a new result about how many primes there are up to x. I proved that there are at least log x primes up to x. Now, when you consider that Euclid got log x, and I have log x, it looks like my result is worse. But you don't appreciate how much worse it is until you look at the actual method of proof that I used. And that's the reason I'm talking about this today, is I want you to learn a lesson. So I was using a paper that I found online that you went through and gave results about how irrational pi squared over 6 was. I didn't read the whole paper initially, I just used the results I cared about. And then as I'm writing everything up, I figure it's probably not a bad idea to read the paper. So Not surprisingly, this paper built on other papers, and it used other results. One of the results it used was the prime number theorem, which states that the number of primes up to x is about x over log x. So one of the inputs in the bound I needed was that there are x over log x primes. Using that, I was able to prove that there are at least log x primes by doing some detailed analysis. There's a faster way, of course, to prove that. If we're assuming the prime number theorem, x over log x is much, much larger than log x. So eventually I was able to clean things up and actually make the result, but it's really easy to accidentally assume something and not realize that you're pulling something in that is using something else. When I was a postdoc, a graduate student showed me their thesis and I had a little fun with them. I looked at it and said, you're very interesting. Do you realize that half your thesis is wrong? And your complete look of shock and horror. And then, I let him sweat for a little bit and said, you're quoting, a certain paper. I know that paper quite well. They state in the introduction, we assume k is congruent to 2 mod 4. If k is congruent to 0 mod 4, the calculation is handled similarly. Or maybe it was the other way around. And so he has an extra minus sign that has to come in for half the values. That paper should have clearly stated again before the theorem, we're assuming k is 0 mod 4, so that you don't accidentally pull something out by mistake. So in terms of, this is one of your last math classes, this is one of your capstone classes, things I really want you to learn. It's okay if you don't understand every line of something that you're using, but you should at least be aware of what's being assumed and what's being used. And when you have papers building on papers, it can often be very hard to trace back just exactly what's being assumed. And can you trust all the subsequent stuff? Because if there's an error early in the chain, it can propagate. So these are examples of generating functions. And for the Riemann zeta function, you can teach multiple courses on this in terms of all the connections you can do. What I want to do is I want to give you a little bit of a sense of other things that can be done with generating functions, and different generating functions turn out to be easier to work with. This is just meant to be a first course and just a quick exposition. I am not going to go into great detail. If anybody wants to see more detail, I will share with you chapters on this. This is called the circle method. And I don't have time to do the method justice. I also don't have time to show where the circles come from, but I will just show you a general idea. So we have a conjecture. Any integer 2m can be written as the sum of 2 primes if m is large. Anybody know what large means? So it's conjectured that every large even number can be written as the sum of 2 primes. I'm sorry? Yes. So as long as m is large, like 4, then you can write m as the sum of 2 primes. This is open. What's known is 2m plus 1 can be written as the sum of 3 primes if m is large. Anybody want to guess what m has to be here? Three. Because if you do 5, that would start you off at 11. So the question is, can you write 9 as the sum of 3 primes?
Oh, I see.
Yep. So you can write 9 as 3 plus 3 plus 3. You can write 7 as 2 plus 2 plus 3. So it's known that as long as m is at least 7. Now, these problems were considered, horrible problems by many for a long time because primes are multiplicative objects and we're asking additive questions. So again, this is a class on problem solving. My goal is not to have you leave this class well-trained to do specific problems. That's not a useful skill unless you want to be, a trained monkey working in a specific area. What I want you to leave this class is knowing how to attack something new. And that's why for Friday, I'm going to give you, actually, might as well just pass this out now. I'm going to just, don't look at the problems now. So turn it over, take one, Don't look at these problems. And I'll email you directions on how to do it. So don't look at them now. These are problems you hopefully have not seen before. And the idea is to just, how do you attack things you haven't seen? That's the skill I want you to get out of this class. And a lot of times, things we have done are useful in general, but may not be useful in particular in terms of attacking something. But think about, how have we attacked problems? Can you do some special cases to build intuition? Can you use a parity argument? What kind of things have we done? Can you do induction? And so what I want to do is I want to talk about how you might try to attack a problem like this. And so the idea is to consider a generating function. We're going to let fn of x be the sum p less than or equal to n of e to the 2 pi I px, where e to the I theta is cosine theta plus I sine theta. And it's better if we have a log p weight in front of each of these terms. It just makes things technically easier if we have the log p weight, because primes are better counted with a little bit of a bias. I don't want to get into that now. I want to just talk about how you can use generating functions like this to attack problems like this. So this is the Goldbach conjecture. But you can do this for a variety of problems. Okay. Let's consider, has everybody seen e to the I theta before? Everyone has seen e to the I theta, okay. So the first time I was teaching a senior seminar at Williams, a third of the class had not seen that. So let's take fn of x and let's square it. So this would be the sum p less than or equal to x e to the 2 pi I p, let's do p1 of x, and then the sum p2 less than or equal to x e to the 2 pi I p2 of x. So this will be the sum of a n n e to the 2 pi I n x, where a n of n is equal to the number of pairs p1, p2, such that p1 plus p2 equals n, p1, p2 less than or equal to n. Okay, so if you multiply things out, how can I get a non-zero coefficient? Well, I've got to have something from the first hitting something from the second, right? And if they hit, I get P1 plus P2. So the only values of little n that will be non-zero when I multiply everything out will be the little n that can be written as the sum of 2 primes. If I wanted to talk about sums of 3 primes, what would I do? Yeah, I would consider f of n cubed. So this is going to give me how many ways little n can be written as the sum of 2 primes, where the primes are at most big N. Okay. Note a n of n equals a of n if n is less than or equal to n. A of n, well, we'll put like maybe a superscript 2 here, is the number of ways to write n as a sum of 2 primes. So if my number little n is no more than big N, this is going to just give me the total number of ways of writing my number as a sum of 2 primes. Because if my number is 18, I'm not going to use a prime larger than 18 in its decomposition. Okay, so now consider the integral from 0 to 1 of e to the 2 pi I n x. And this is the same as the integral from 0 to 1 of cosine 2 pi n dx, oops, 2 pi n x dx plus I integral 0 to 1 sine of 2 pi nx dx. Can anybody tell me what these integrals are? Zero and zero? Almost, you're close. So I have sine 2 pi nx, I have cosine 2 pi nx. What's the period of cosine 2 pi nx? Not n, you're close. 1 over n. So every time x increases by 1 over n, I go through a whole set of 2 pi. So if you integrate cosine x from 0 to 2 pi, what do you get? 0. If you integrate sine from 0 to 2 pi, what do you get? You also get 0, right? Sine and cosine are the same function, they just shifted by 90 degrees. So it seems like this integral should just be 0, because we have an integer number of periods. So if n is an integer, is this always going to be 0, or is there any integer n we have to be careful about? If n is 0, then you get the cosine of 0. What's the cosine of 0? 1. So if n equals 0, you always get 1. But the sine term, even if n is 0, is still going to be 0. So this equals 1 if n equals 0, and 0 if n does not equal 0, an integer. Okay. Why is this useful? If we integrate from 0 to 1 of fn squared of x e to the negative 2 pi I n x dx, this is the integral from 0 to 1 of the sum of an. Oh yeah, I'll use an m here. An of m e to the 2 pi I n x times e to the negative 2 pi I mx dx. Can I switch the integral and the sum? The sum is finite and the integral is finite. So this is going to be the sum, n goes from 0 to 2n of an of n. Then we'll have the integral from 0 to 1 e to the 2 pi I n minus m x dx. What does that integral equal? Zero unless n equals m. And when n equals m, we then just get over here, this will just be an of m. So this integral tells you the number of ways you can write m as the sum of 2 primes at most n. We have reduced Goldbach, we have reduced to can you write an even number as the sum of 2 primes to evaluating this integral. This integral is incredibly painful. It would take maybe 2 weeks to just really go through all the stuff that we need to evaluate this integral. And this is why it's called the circle method. Because instead of looking at the interval from 0 to 1, you can think of it as your angle is going from 0 to 2 pi. It was initially done with angles. It's a little bit more convenient to do it with 0, 1, but the notation has survived. And you split this integrand, this generating function, up into places where it's large and small, and you approximate the integral. If we want to show that we can write m as a sum of 2 integers, what do we need to show about this?
Always 1.
Nope.
Greater than or equal to 1?
Greater than or equal to 1. So if we can show that the integral is greater than or equal to 1, then we know that there has to be at least one representative. What if we show the integral is greater than or equal to 0.3275? We know it's an integer. And so this is one of the wonderful methods of proof we have. If you know something is an integer, and it's greater than 0, it must be at least 1. Or, and we're going to use this potentially later in the semester. If not here, I'll definitely use it in my other class, 317. If you have a odd integer, a positive, a non-negative odd integer, what do you know about it? Greater than or equal to 1. So if you know that the number of elements in a set is a odd integer, then the set is non-empty. And this is a very powerful technique to prove the existence of something. You prove that there's an odd number of elements, therefore there must be at least 1. And so here, this is a great example of generating functions. Again, this is a capstone class. I want you to be a little bit aware of what's out there mathematically. There are ways to tackle problems like this. It's some of the most beautiful mathematics I've ever seen. When I was a postdoc at Ohio State, one of my colleagues asked me, what do I think is the most beautiful idea in mathematics? And I answered the method to solve this problem. And he said, I'm young. It's been 20 years and this is the most beautiful thing I've seen in terms of giving you a hand on problems like this. So again, if anybody is interested, I'm happy to talk more about this. But I wanted to use this as an opportunity to transition to something that you may not have seen that you should have seen, as well as an opportunity for those who are looking for some stuff to do. Yes? The ternary Goldbach conjecture is solved. There's been a posted proof that every large odd number can be written as the sum of at least 3 primes. And the proof is a mix of theory and computation. So you take care of the small values up to 10 to a reasonable power by brute force. And then you do the rest by some theory. And so one of my mathematical siblings, Harold Hilfgott, was the one who finished the proof of the ternary Goldbach problem. Binary Goldbach is still open. You can also use this method to prove heuristically how many twin primes there should be. Your primes that differ by 2. Well, I think it's prime cousins if you differ by 4. I'm not sure of all the different terminology anymore. And again, in problems where you can't rigorously establish the integrals, you can calculate the expected main term, and then you have a lower order term, which you believe is a lower order term, which you believe is smaller, but it's very hard to show. And again, if people are interested, happy to talk more about that. What I want now is talk about a theorem that was mentioned a moment ago, Fubini's theorem, or sometimes you might hear the Fubini-Tonelli theorem. You should have seen this in Calc 3 at the very least. The integral, f of xy dy dx equals the integral of f of xy dx dy if f and region are nice. Has everyone seen some version of this, that you can switch the order of integration if your function and region are nice? All right, does anybody remember the conditions? So can we always switch the order? I'm sorry? F does not need to be continuous. You are okay if the integral of the absolute value of f is finite. So if the integral of the absolute value is finite, then you can switch orders. So how many of you actually saw a proof of this in some class? Okay, this is one of the most important theorems we have. I mean, when you think about multivariable calculus and integration techniques, there are 2 integration techniques we have in multivariable calculus. One is switch the orders, and the other is change variables. So what are the 3 most popular change of variables? Three big ones that they force you to learn. They force you to learn the determinant of the Jacobian for how dx, dy, dz, or other things transform. What are the big 3 coordinate transformations for multi? Polar, which has a horrible name. Cylindrical, which has a much better name. And spherical, which also has a really good name. It's very hard for me to hide that this is going to be a spherical coordinate problem. Consider a sphere of radius 5. I wonder if this would be a good. Right? It's pretty obvious what to do there. There are other changes of variables you can make, but these are a little bit harder. So what I want to do is for the rest of today is talk a little bit about when are you not allowed to do what you want to do? When can you not switch the order of operations? So I am currently writing a book on operations of order and when you can and cannot switch. And so if anybody is interested in doing some mathematical writing in place of some of the stuff for this course, let me know. Absolutely happy to do trades like this. But the point of this is to just really drive home how careful you have to be. So what I want to do instead, is I'm going to give an example where the sum over m and m of a m n is not the sum over n, sum over m of a n m. So I want to show an example where you can't switch orders. This is not the same as giving you the proof of when you can switch orders. It's enough to just show you that you have to be careful. So what do you think must somehow come into play for this problem? There must be what? There must be an infinity. So infinities are the danger signs in mathematics. Whenever everything is finite, usually it's not too bad to justify whatever you want to do. You know, the derivative of a finite sum is the finite sum of the derivatives. That's not so bad. You can do this by induction. But as soon as you have the derivative of an infinite sum, is that the infinite sum of the derivatives? That's much harder. And so there must be an infinity coming to play. Now, for Fubini's theorem, we normally state it with a double integral or a triple integral. I'm doing it in terms of two sums here. The more general version is when you have some kind of measure space, some kind of generalized integral. And the integral could be a sum, it could be an integral, it could be some could be integrals, some could be sums. It's just easier for me to write down the example. If you don't like the sums, smear things out, not a big deal. All right. So what I'm going to do is I'm going to start drawing a subset of infinitely many points. Given that we only have a finite amount of time, this is not going to work that well. Although I wonder, this is the advantage of, oh, come on. Oh, no. Why is it not letting me move them? Wow. Oh, there we go. Okay. So here's my dots going off to infinity. And so here is the point. Here's the point 0, 0. Okay. And then this would be 1, 0, 2, 0, 3, 0, 4, 0, going off to infinity. This would be the point 0, 1. This would be the point 0, 2, 0, 3, 0, 4, and going off to infinity. Okay. And now I'm going to define the terms of my sequence. It's going to be +1, -1, and then 0 for the rest of eternity. 0, +1, -1, and then 0 for the rest of eternity. And then 0, 0, +1, -1, and then 0 for all eternity. Now let's think about the sums. What happens if we do the column sum first? What are all the column sums? 0. So column sums are all 0. So when we look at AMN, if we do n first, we're doing the column sums, right? So the sum over m, sum over n of AMN equals 0. What about the row sums? One then 0. First row sums to 1, rest 0. So the sum over n, sum over m of AMN equals 1, and these are not the same. So this is the easiest example I know of you cannot switch the order of integration always. And again, if you don't like this, take this function and make this a continuous function by saying, all right, let's make it like a cone coming up with a circle of radius 1/2 coming up to height 1. And then here we'll have a cone of radius 1/2 going down to -1. And so if you do it like that, it's now going to work out perfectly. So this is a great example of how you have to be careful. Let's do another example. Fn of x be defined as follows. Here's 1 over n, here's 1 over 2n, here's 3 over 2n. And I'm going to define, and here's 0. And I'm going to define my function as follows. It's going to go like this, go up, and come down, and go like this. Right? What's the width of this? Not 1 over 2n, 1 over n. So I'm going to make the height 2n. So what is the area if I integrate Fn of x from 0 to 1? What do I get? I get 1. So if I take the limit as n goes to infinity of the integral from 0 to 1 of Fn of x dx, what will I get? One. If for every value of n, the integral is 1, then what's the limit as n goes to infinity of 1? It's just 1. What about the integral from 0 to 1 of the limit as n goes to infinity of Fn of x dx? So I want to pass the limit inside the integral. What do I get for the limit as n goes to infinity of Fn of x for any fixed x? 0, because eventually, if x is 0, the function is always defined to be 0. If x is not 0, eventually 3 over 2n is less than x. So does everyone agree that as n goes to infinity, for any fixed x, Fn of x is going to be 0? So if x equals 0, get 0. If x is not 0, get 0 once 3 over 2n is less than x. So this is just the integral from 0 to 1 of 0 dx. This is probably the nicest integral I could give you. Yes? In fact, it's so nice we can even do it with Viemann sums. Upper and lower sums can get 0. So these are unequal. So what this means is you can't just pass a limit through an integral. So how many of you have taken measure theory? Okay. If you are thinking of graduate school in mathematics, measure theory is one of the classes you want to take. And there are a whole slew of conditions on when can you switch the integrals. So if you've taken measure theory, do not answer. Can anybody think, what is going wrong? What is causing a problem here? Because you would hope that the limit of an integral should be the integral of the limit. It's not. We've got an example in front of us that shows us that it's not. What do you think is responsible for this problem? So what do we say is often a source of danger? Infinity. Can anybody see an infinity here? Okay. Where is that creating? I mean, we're always going to have n going to infinity. I mean, yes, we do. We have a limit going on, but where is the infinity in this problem? The spikes get infinitely high. The infinity is the spikes get infinitely high. It's not uniformly bounded. So how many people here have taken real analysis? Okay. I can't put my hand up for abstract algebra, but I have taken real analysis. So did you do uniform continuity? And so, normal continuity is given an x, I'm sorry, I want to try to figure out, is the function continuous at x? So for all epsilon, there exists a delta, which can depend on epsilon and x. That's normal continuity. Uniform continuity is given an epsilon, there is a delta that depends on epsilon, but works for all x simultaneously. So in analysis, we often try to do things uniformly, trying to do things all at once. And the problem here is there's no nice function that I can find that will always bound fn of x for all n. Fn is spiking upwards. So if people find problems like this interesting, there's a whole slew of problems I can do that just all of your intuition of what should happen does not happen. That unfortunately in a problem like this, even though each one integrates to 1, the limit integrates to plus infinity. So yeah, I'll end with something to think about because I'm assuming we're not going to have a meeting on Friday because of Mountain Day. So consider the following. Can we find a positive, well, let's say non-negative, a non-negative function f on the interval 0 infinity such that the integral from 0 to infinity of fx dx, integral 0 to infinity fx squared dx, dot, 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 integral 0 to infinity fx to the 2021 dx are finite, but the integral from 0 to infinity of fx to the 2022 dx is infinity. So something to think about is, can you find a function where all of these first integrals are finite, and then all of a sudden at integral f of x to the 2022, you get an infinity? Do you think there is anything special about 2022 here? No, I should be able to give you any positive integer, and I want a bunch of them to be finite in the beginning, and then all of a sudden I want something to become infinity. So try to think and see, can you come up with an example? Now we already have an infinity in play. What's the infinity in play? Yeah, the integral is going from 0 to infinity. So that may be the only infinity we need. There's at least enough here that we have a chance for danger. But we might want other infinities at play as well. So again, I'm trying not to give you too much reading for this course. I'm trying not to give you too much problems. I really want to use this to try to put together a lot of the things you've seen over your years at Williams, and just see how things connect, and just talk about how do you attack new problems. That's what we're training you for here. We're not training you to be the trained monkey, although if you want to be that, absolutely fine. There's a lot of good trained monkey jobs out there. It's how do you handle something new? All right, so I think this is a good place to stop. So I will wish everyone a good day.